How am I doing for time?
Yeah.
So can we see this in any other systems? Is it specific to coronary with this large diamagnetic susceptibility? Carbamazepine is, if you worked in pharma, you would recognize this instantly. It's a very, very well-studied drug, especially structurally. It's an anti-epileptic drug, billions of dollars of sales. Has four known native anhydrous forms. There is a fifth one that's grown up epitaxially, but there's basically four forms. And this is the CSP here, crystal structure prediction. So each one of these points are a new energy minima for this crystal to exist. And the known forms are circled with blue circles. Form 3 is that red one at the bottom. That's the one we see if we just dissolve it in ethanol and let the ethanol evaporate. And the other forms are found by heating it up, cooling it down, additives, different solvents, that kind of thing. But it's a very well studied drug. So I started looking originally for this little black data point down the bottom, which there's a whole other reason why that's difficult to get, but it seems to be the lowest energy. Why no one's seen it yet is I mean, it makes sense, but I'm not going to go into that here. Anyway, so I did the low temperature powder diffraction on it, again, to see if there was any kind of phase transition from one to the other. And what I see is nothing. There's just expansion, contraction, that's it, no phase transition whatsoever. So am I to expect anything to change with carbamazepine? So back in Bristol, this is where we designed this piece of kit. This is basically a copper block with like a horseshoe-shaped holder. We slot the cuvette in like this. We push it into the copper block. This is a water pipe in. This is a water pipe out. So we flow water through the copper block nice and fast so we can keep the temperature nice and stable. So we use a water heater to control the temperature of the water, and that water then controls the temperature of the copper block. We've also got an optical cable going through the middle, so we can also, again, measure the point of crystallization. But when we put carbamazepine in a cuvette, in the magnet, what do we get? What we see is we do get polymorph selectivity. We go from form 3 to form 1. Form 1 is characterized by this fibrous form, long, high aspect ratio needles, and form 3 is characteristic of these, these rhombohedral block-like crystals are characteristic of form 3. So we get form 3 out of the magnet, form 1 in the magnet. So great, it looks like we've got another system which we have polymorph selectivity. Do we have the undercooling? Initial results would suggest we do. This is a lot messier than the data you saw a minute ago, but this is only between 0 and 2.2 Tesla. We definitely have that drastic decrease initially, and maybe some kind of upswing as we go to higher fields, but this needs more work, more data needs to be collected. However, as I said, it was a very well-studied material, and what we know about this is that this is a paper published by Parambil, 2017, I think, who basically did a concentration study with carbamazepine and said the more saturated your carbamazepine solution, the different forms you get. So you get form 3 at low concentrations, form 2 and form 3 concomitantly as you increase the saturation, and form 2 at the top. We were getting form 1. So it looks like what we may have been doing is getting the suppression of crystallization into that little wedge again, and increasing the supersaturation beyond which they can do with just solvent-mediated means. We're suppressing the crystallization, increasing the supersaturation, and making form 1. This is just a flow chart of how we've been getting the different forms of carbamazepine. this is now two systems in which we've seen it work. A difference in the carbamazepine unit cells, Form 1, Form 3. This again was work by UCL. Form 3 has this inversion cup motif, which goes through the crystal, and all of the hydrogen bonds point in the same direction, which is kind of interesting. Form 1 has these kind of offset stacks. Is that significant? Well, the susceptibility calculations would suggest that the form we get out of the magnet has a higher magnetic susceptibility than that grown in the magnet. I mean, make of that what you will. It looks like the magnetic anisotropy of the unit cell may not be an important factor when growing these crystals. Just a quick note on charge transfer complexes and why polymorphism is important in these systems. Charge transfer complexes in organic crystals are very important. They've been superconductors if you pick the right combination of donor and acceptor in these co-crystals. And specifically, we have here stoichiometry of 1:1 in these co-crystals. Now, technically, you can change the polymorph of these co-crystals also and drastically change the charge transfer properties. So a mixed stack, which basically has this alternating molecules in each stack, has typically a lower conductivity than segregated stack, donor and acceptor. So if we can take something that grows in a mixed stack and make it a segregated stack, possibly using magnetic fields, then we can increase the charge transfer properties of these crystals. So effectively, just to kind of summarize where I think the mechanism of this lies, because we're still not at the bottom of it, is we dissolve material up to a saturation point, and then we remove any nucleation sites that we can. So we filter with the smallest filter we can, keeping the temperature elevated. Then we make it sealed and we start to cool. So we get this supersaturation again, but we're able to push the supersaturation further and further down the temperature gradient. So it has a greater supersaturation than this, okay, which is important because it's probably where the selectivity of the polymorphism lies. So we get Form A at lower supersaturations, Form B at higher supersaturations, and the magnetic field is allowing us to access these higher supersaturations. So to summarize that, all properties associated with a bulk molecular crystal are a function of the interactions between molecules. You change those interactions, you turn a molecule over, things change. Any property can be affected by this. Another thing that's important is that if you're doing an experiment and you're growing a crystal in situ, in a microscope, in a magnetometer, in an NMR machine, sometimes there is an intrinsic field present. So if you're growing a crystal with an intrinsic field present, you have to take that into account. You can't assume that the crystal you want has grown because there's a magnetic field present. So if you want the orthorhombic form of rubrene grown in a capillary at the bottom of the squid magnetometer, you can't assume that it's the orthorhombic form that's grown because the field could be making a difference in changing the polymorph. It seems that there's preferential growth of the metastable polymorphs under field, and suppression of crystallization being observed. Looks like we're getting these metastable forms because we're pushing the supersaturation that far, and that magnetic fields might be a means of reaching these supersaturations that have yet been unattainable by other means. Just things that we're looking into at the moment. We've got a liquid cell over in Limerick, a liquid cell sample holder for a transition electron microscope, which is very exciting, so we can watch these crystals growing. We also have NTA, which is nanoparticle tracking analysis, which might get to in a second. How much time do I have? Yeah, okay. And identifying and characterizing model systems based on the interactions involved. So we know that the field is having an effect in these samples nucleating. What we need to know is why are they having an effect. So instead of just growing crystals, maybe we're going to try putting things in which exemplify a particular type of interaction. So something that's massively hydrogen bonded. If we put that into the system and it won't grow, does that mean the magnetic field is suppressing hydrogen bonding? If we've got something that exclusively pi stacks and it doesn't grow, does it mean the magnetic field is suppressing pi stacking in the system? But we're going to get to the bottom of it. I've got a year left of my postdoc to do so. Just to thank some people that have helped me quite a lot. My group, Simon, Charlie, Vicky and Nicole back in Bristol, have been invaluable with getting the lab set up and getting sample preparation done. UCL, Rui is the guy that did all the calculations. He's an absolute wizard with it. These are the guys from Radboud.